Hi students, welcome back. Today we are going to look at the 0 1 matrix problem on LeetCode. Let's look at the problem statement first. So the problem statement says we are given a m by n binary matrix meaning matrix having zeros and ones. We have to return the distance of the nearest zero for each cell. So given a binary matrix, we have to return the distance of nearest zero for each cell. Okay, the distance between two adjacent cells is 1. So if you have to go from one cell to another, the distance is 1. Okay, so let's look at an example. So in this example, the input matrix is 0 0 0 0 1 0 triple zeros. So clearly to reach 0, you don't have to do anything. So the distance is 0. But for this one, to to reach a nearest 0, you have to travel at least one cell, which is why in the output matrix only this one is 1 and rest all are 0. Okay, let's look at another example. So here in this example, similarly for all zeros, the output matrix will still be 0. So all zeros are 0. Okay. For this one, the nearest 0 can be any of these. So the distance would be 1 because you have to travel one cell. Similarly, for this one, there is a neighboring 0. For this one, there is a neighboring 0. Whereas for this one, there is no neighboring 0, which is why it has to travel two cells, which is why the distance for this would be 2. So the output of this would be this matrix. Okay, so if you look at this problem, you can think of this as a graph problem. Graph problem with neighboring nodes as connected nodes. Okay, so what we have to find here is distance from nearest distance from 1 to the nearest 0. Okay, we could either employ BFS or DFS, but we are looking for a shortest path, and BFS is a level order traversal, which is why you will get the shortest path from one node to every node in the path, which is why we have to pick up BFS in this case. Okay, so the algorithm we will follow is uh, in the BFS, we will first start with all the nodes which are 0. Okay, so our initial array would be, okay, we will first, so this is our result array. Okay, in the result array, nodes with 0 are already 0, whereas with 1, we have to calculate the value for this. So initially, we will consider these as -1, which means they are unvisited and we have to calculate them. And all the visited nodes, we will put it in a queue. Okay, so which means this queue will have 0, 0, 0, 1, okay, 0, 2, okay, 1 comma 0 and 1 comma 2. Okay, at every point we will take the first node in the queue. Okay, and so initially we'll take 0 comma 0. Okay, what are the neighbors of 0 comma 0? 0 comma 0 has 0 comma 1 and 1 comma 0 as neighbors. Okay, for each neighbor what we will do is we will see if it is unvisited. If it's not visited, then we'll calculate its distance and we'll add it to the queue. If it is visited, we don't have to do anything. In this case, both 0, 1, 0, 1 and 1, 0 have 0 value, which means they are visited. So we don't have to do anything. So we finished processing 0, 0. Now we take 0, 1 from the queue. Okay. So for 0, 1, again neighbors are for 0, 1, neighbors are 0, 0, 0, 2 and 1, 1. Okay, 0, 0 is already processed, 0, 2 is already processed, whereas for 1, 1 it is unvisited. So we have to calculate the distance for 1, 1. So what will be the distance? Current node distance plus 1, because the distance to travel a cell is 1, which is why it would be current node distance plus 1. So the current node distance is 0 plus 1. So this becomes 1. Okay. And we will add this to the queue. Okay. 1 comma 1 also gets added to the queue. Now in the next iteration, we'll pick up 0 comma 2. 0 comma 2 is this node. 0 comma 2's all the neighbors are processed. There is nothing to do. Then it is 1 comma 0. In case of 1 comma 0, 0 comma 0 is already processed. 1 comma 1 is already processed. But 2 comma 0 is also a neighbor and it is not processed. So we calculate the distance. Distance is current node's distance plus 1, which would be 1. And we will add this to the queue. Okay. So we will also add 2 comma 0 to the queue. Okay. Now we pick up 1 comma 2. 1 comma 2, which is this node. Neighbors are 1 comma 1, which is already processed, and 2 comma 2, which is not processed. So for 2 comma 2, we will calculate the distance and again we will add it to the queue. Okay. Now 1 comma 1. 1 comma 1 has 3 neighbors. Okay. 1 comma 0, which is already processed. 1 comma 2, which is already processed, and 2 comma 1. For 2 comma 1, the distance would be current node's distance plus 1, which would be 2. Okay. And we will add 2 comma 1 to the queue. Okay. Now when you pick up 2 comma 0, all its neighbors are processed, there is nothing to do. For 2 comma 2, all its neighbors are processed, there is nothing to do. For 2 comma 1, all its neighbors are processed, there is nothing to do. Okay. So this is our result. So the result is 0 0 0 0 1 0 1 2 1. Okay. So what is the time complexity of this approach? It takes order of mn, which is the BFS complexity. Okay. We are not using any additional memory here. So let's look at the source code for this. Okay. So first we are employing BFS, so we need a queue. Okay. Queue. It has to hold the vertices, so it has to hold a integer array. New linked list. Okay. Now we have to process the matrix. So for each cell in the matrix, okay, what we will do is, if matrix of row of column, if the current cell is 1, then okay, we will change it to -1. Okay. Matrix of row of column. So we can either define a new result array and use it, or update the given matrix itself. Okay. Otherwise, what we will do is, otherwise it's already 0. There is nothing, no change of value is required, but we will have to add it to the queue so that we can use this as a initial elements in the array. So what do we add? We add the coordinates. Coordinates are stored as a array. So I'm creating a 2-member array and added it to the queue. So now at the end of this, our initial matrix will be modified with all ones as marked as unvisited with -1 value, and all zeros remain unchanged, but the coordinates of all the zeros are added to the queue. Okay. Now what we will do is, we have to process the queue, take out each element and process its neighbors. So to figure out the neighbors, I am defining something called a direction array. Direction array will give you the coordinates of its neighbors if you add it with the current coordinates. Okay. Now what we will do is, as long as the queue is not empty, okay, as long as the queue is not empty, we will pop out an element from the queue, okay, and we will define the current row and current column. Okay. I took out an element from the queue. I defined the current row and current column. And now for each of these, I have to find the neighbors. Okay. How do we find the neighbors? I will use this directions array. So for each of these things, I will find the next coordinate, probable next coordinate. It might even go out of bounds. So we will have to check for that as well. So first let's write a function to check for out of bounds. Okay. So this will tell us if it is out of bounds or not. So we are just checking for the boundary conditions of the rows and columns. Okay. So now if the calculated new coordinate, which can be the neighbor, if it is not out of bounds, okay, and if it is not visited. If it is not visited meaning if it is equal to -1. Okay. If it is equal to -1, okay, what we have to do? We have to update the neighbors distance, okay, and we have to add it to the queue. Okay. First thing is updating the neighbors distance. Okay. And we have to add the thing to the queue. So we have to add this current coordinate to the queue. Okay. So we create another integer array with these rows next and call next and add it to the queue. So next time we will continue processing this as long as the queue is not empty. Okay. Let's try to run this and see. Okay, we haven't defined a result, so this would be matrix itself. And end of it, we have to return the result. So we have to return the matrix. Okay, so this is accepted. Let's submit this and see. Okay, so the approach is simple. We follow BFS and we take all the zeros as the initial set. So we update the matrix with marking all the ones as unvisited and adding all the zero coordinates to the queue. As long as the queue is not empty, if a neighbor exists and if a neighbor is not visited, if a row coordinate exists and a coordinate is not visited, we will calculate the distance of it and add it to the queue so that we can further process its neighbors. Okay. So this is a BFS approach. Now there is another way in which we can solve this problem using the dynamic programming style. Okay. Uh, so here basically at every point what we are doing is we are finding the optimal value of the distance based on its neighbors. So if we can continuously keep calculating the distance of its neighbors, then that will give us the result. But since there are 4 coordinates, it may not be guaranteed that we calculate the distance of all the coordinates. So the approach we will follow here is we will take a two-step approach. In first step, we will calculate all the nodes distances based on the top and left node. Okay. Then we will go from bottom up. We will calculate all the distances based on the right and bottom and we will take the min of those. This is the dynamic programming approach. So for this again, similar to earlier, initially we will initialize the matrix. So what will we do? For all ones we don't know the value yet. So we will mark them as some max value or infinity. 0 is already 0. So 0 will be same. Okay. Initially, this is how This is how the initial matrix would be. Okay, this is step 0. Now at each node we will calculate the top and left, and we will calculate the distance based on the minimum of top or left plus 1. Okay, so for example, for 0 comma 0 there is no top and left. Okay, so we can assume them as infinity in that case again. Okay, so top and left plus 1 will again be infinity. Okay, even here top and left plus 1, top left plus 1. In case of 0 there is nothing to do. Now if you look at 1 comma 1, minimum of top or left, top is infinity but left is 0. So this value will become 1. Okay, for here also minimum of top and left is 1 plus 1, so this would become 2. Here minimum of top and left, so this would become 1. This would become 2. In case of 0, we don't have to do anything. So after step 1, after the first step of updating based on top and left, this is how the resultant matrix will look like. Okay, 0, 1, 2 and 1, 2, 0. Now we have to update this based on the right and bottom. Right and bottom is right and bottom. We have to go bottom up now. While doing this, we have to also take the whatever we have processed earlier into consideration, which is why we have to take the minimum of whatever the cell is having, or minimum of right and bottom plus 1. Okay. Again, in case of 0, there is nothing to do. So 0 would still be 0. Now, if you look at this value, right is 0, bottom is infinity. So the minimum of them is 0. 0 plus 1, 1. The current cell value is 2. Minimum of 1 and 2 is 1. So this becomes 1. Okay. Now, if you look at this value, it is already having the minimum value, so you don't have to change anything. For this one again, minimum of right and bottom is 0, 0 plus 1, 1. Its current value is 2, so we will update this. Okay, here it is already having minimum value. Because top and bottom are 1, 1, 1 plus 1 would become 2, whereas currently it's already having 1, so we'll leave it as 1. 0, we don't have to change anything. Now in case of this one, right is infinity, bottom is 1. So this becomes 2. Okay. Again here bottom is 1. This is the minimum value 1 plus 1. So this becomes 2. Okay. In here right is 2 and bottom is 0. So the minimum is 0 plus 1. So this becomes 1. So after the second pass, okay, which is step 2, now our matrix will become 1, 2, 2, okay, 0, 1, 1, 1, 1, 0. Okay. So in first step, we have calculated the minimums based on left and top. Okay. And in the second step, we have calculated the minimums based on the right and bottom, and also whatever it has the current value. So by doing this two-step approach, we are basically figuring out the minimum value of all the four sub neighbors plus 1. So that will give us the answer. Okay. Let's look at the implementation for this as well. Okay. So initially we will need some max value to put in the matrix. Okay. Let's define a max value, some 10,000. Okay. And let's define length of the matrix m by n, just for simplifying our calculations. Okay. Number of rows and number of columns basically. Okay. Now we have to find the top and left, top and left. So we have to go in an increasing order. So we will go from row equal to 0, row less than. So we are going from 0 comma 0 to m by n. Okay. Initially, let's initialize top, a variable top with some max value. Okay. Let's initialize a variable left, top and left with the max value. Okay. So if a top exists, that means if row is greater than 0, okay, if only if it is greater than 0, a top will exist, correct? Then we will get the top value, otherwise it would just be max value, which we represented as infinity while working on it. Okay, we will get the top value. Similarly, if a call exists, I mean if a uh, left exists, left will exist only if column is greater than 0. We will take left equal to matrix of row of call minus 1. Okay, so we are getting the top value and left value if it exists. If not, it will have some max value. Okay, now the current value would be, what will it be? Min of these two plus 1. So max dot min of top comma left, okay, plus 1. Okay, now we have completed our first pass. Okay, in the second pass we will do a similar thing, but we will do bottom up. So let's copy paste this thing. So we will do bottom up. So what we will do is, we will start with m minus 1, okay, greater than or equal to 0, and we will do row minus minus. Similarly, column would be n minus 1, okay, greater than or equal to 0, and call minus minus. Okay, okay. So one thing I missed here is, we have to do this processing only if it is not 0. If it is 0, we don't have to do anything, correct? So we have to add this condition as well here. Okay, yeah. So now we are going bottom up, so it won't be right, it won't be top anymore. Now we will call this right and bottom. Okay, now when will we have a right? When row is less than m minus 1. Okay, and to calculate right, we will do a plus 1. When will we have a, so this would be not top but right. Okay, and when will we have a bottom? When it is less than n minus 1. Okay, here in this case it would be plus 1. Okay, now in this case earlier we just did max dot min of this and plus 1, but here we also have to take the current value into consideration. So we have to do max dot min of, okay, current value, which is matrix of row of call, okay, and whatever calculation we are doing. So this should give us the updated value. Okay, at the end of this we have to just return the matrix. So in the second pass we are going from bottom right to, okay, this is right and bottom. Okay, let's submit this and see. So this would be much faster than the earlier one because there are no queues, there are no additional memory and all that. Okay, so here the time complexity would be just whatever we are traversing, which is order of mn. Okay, and no additional space is required. In earlier case, we are taking a queue, so it will need a additional space of order of mn. Okay, so it is a little bit difficult problem. Please go through it multiple times and do a dry run on your own. If you have any questions or queries, do leave a comment. Please like, share and subscribe. Thank you.